Okay, in here we have to prove, given a group like this, if H1 and H2 are subgroups of G, then we have to prove that so is the intersection. And more general than this statement, we have a set of indices, right, like this one here, and then we have that Hi is a subgroup of G for every choice of the index in this set, then the intersection for all the indices of these subgroups is also a subgroup, right? We have to prove that. Okay. Actually, I'm going to prove the second because the first is just a particular case of the second. So we prove the second, we're done. Right. We're going to prove this by the standard method of characterization of any subgroup. H is a subgroup of G, right? If and only if you take x and y in H, then x times y minus 1 belongs to H, right? So we're going to prove this, right? Okay, so let's consider this set. I'm going to call it W, right? So let's say that we have two elements, x and y, in W. Now this is an intersection of other sets, right? So if they are in the intersection, that means that these two elements are in every one of the elements of the sets of the intersection, right? So that means that x and y belong to Hi for every I in the set of indices, right? So they are in every one of these sets here. All right. But every one of them is a subgroup, okay? Which means, according to this, that x times y minus 1 belongs to Hi, again, for every I in the set of indices, okay? Right. If you have this element which belongs to all the sets Hi, then it also belongs to the intersection. So x, y minus 1 belongs to W. So W, which is just this intersection, must be a subgroup. And therefore, we have proven this sentence, this statement, and this one, as I said, is just a particular case of this one in which you just have two indexes, right?